Now let's try an example. So, example. Find the most general antiderivative of each. So we'll start with A, which will be f of x equals sine of x. So to do this, we need to think of what trig function is sine x the derivative of. Well, we know that if we take the derivative of cosine, it equals negative sine x. Since we know that, we got to think about the patterns and the signs. So if we take the derivative of negative cosine x, we get sine x, which would look like f of x capital equals negative cosine x. We can also check this by taking the derivative of f of x, which would give us f prime of x equals the derivative of negative cosine x, which is sine x. So an antiderivative of sine x is negative cosine x. We then need to apply theorem 1. So g of x equals negative cosine x plus c. That gives us the most general antiderivative.
So moving on from that, we can now go on to part B of this example. In part B, we will do f of x equals 1 over x. For this, think of functions that equal this when you take the derivative. So we can recall that d of dx, parentheses ln x, equals 1 over x. And we are familiar with this one. We also know that d of dx of ln absolute value of x also equals 1 over x. Now we need to find the intervals on which these functions apply. For ln of x, we know that ln of 0 does not exist, and it cannot be negative. So we get the interval of 0 to infinity, not including 0. For ln absolute value of x, since the absolute value is there, we are allowed to use a negative, but 0 does still not exist. So for ln absolute value of x, the absolute is there to allow that negative, and is everything except 0, which gives us interval negative infinity to 0, u 0 to infinity. So the general antiderivative of this would be capital F of x is equal to ln of x plus c1 if x is greater than 0, and it's also equal to ln of negative x plus c2 if x is less than 0. We need that negative sign there so that it can act as the absolute value. Next, we'll start with example C, or we'll move on to example C. So example C will be f of x equals x to the n, where n cannot equal negative 1. where we use the power rule to discover an antiderivative of x to the n, like we used in the general example. Using that same equation, we would get that capital F of x equals x to the n plus 1 over n plus 1. And we can check this by taking the derivative of this function using the quotient rule. So then we would do this by doing d over dx and writing the function x to the n plus 1 over n plus 1, taking the quotient rule, which would keep the bottom the same, which is n plus 1, then use chain rule on the top, which is n plus 1, x, n plus 1 minus 1, which will just give us x to the n, minus, take the derivative of the bottom, which will just give us 0, times, leave the top alone, all over the bottom squared. When you clean this up, you can see that the n plus 1's on the top are squared, and it's times x to the n over n plus 1 squared. And those two will cancel out, and you're left with x to the n. So then, the general antiderivative of f of x equals x to the n is capital F of x equals x to the n plus 1 over n plus 1 plus c. You have to remember the c. We have to realize, though, that this is valid for everything n equal to or greater than 0. Since f of x equals x to the n is defined on an interval, if n is negative but not equal to -1, it is valid on any interval that does not contain 0. Because if you plug in 0 into x to the n, it gives you 1. So the interval would be -infinity to -1, u, -1 to 0, u, 0 to infinity.